There's another story about ESQL, because everything in software always obviously ends up with naming. And my biggest contribution as a CTO now to Elastic is about naming things. And my suggestion to call ESQL was to call it Aqua, because then people will call it Aqua Lung, and I would hear like the Jethro Tull thingy running behind the scenes. But there's also an interesting French connection to it, because Jacques Cousteau invented the first aqualung, which is like the breathing, the way that people dive today, the self-sustaining breathing stuff. And he called it aqualung as well. So anyhow, I got outvoted, and now we have a very boring name called the SQL instead of a fun one called aqualung. Anyhow, so I'm here to talk about stateless Elasticsearch, and it's funny because 10 years ago I didn't know that that's what we spoke about, but I stood there and tried to explain to the team about nodes and replications and things along those lines. So it's kind of like really closing a circle in terms of how Elasticsearch works and how data is shipped. So I'll explain a bit about how it works. I'll keep it very high level, and then open it up for questions. How many people here know a bit about how Elasticsearch works, how it moves data, replication, things along those lines? Okay. So I'll go over it, and apologies if it gets like more technical than it should. But when we sat down and wrote Elasticsearch and ended up building it, the inspiration for Elasticsearch itself was around the existing state-of-the-art data storage out there. NoSQL was a thing, and things from CouchDB to React to a few other, like Cassandra, other NoSQL solutions out there. And a big part about dealing with a system that stores large volumes of data is how do you take 10 machines, 20, 30, 50 machines, and shard the data itself and make sure that the system keeps the data safe through replication and high availability. How do you scale the system to support all the volume that you need to do? And I think one of the nice things about Elasticsearch was that it made it easy for a search engine. And one of the things that makes it interesting for a search engine to scale, especially if you think about it like as a data store versus just like something that sits on the side and searches data while other things store the data or something like that, is that it's a very rich experience that you end up getting with the search engine. Things from vector search to geo search to all the things that Adrian just spoke about in terms of the richness and vastness of the query experience that you have. And very broad requirements from millisecond response time, because you power as you type searches, to very long-running queries because someone like a threat hunter runs a very expensive query that try to find threats in data in the organization for the past 10 years, for example, or something like that. So when we designed Elasticsearch, the model was actually relatively straightforward. We shard the data, so you look at all the data and somehow you need to slice it one way or another so you can fit into a single machine. And we replicate the data. So when you index a document into a node of Elasticsearch or process, it gets indexed locally, and then it gets replicated to another node, because we want to make sure that we have a few copies of the data to make it safe. The persistency of the data is local disks, right? So it's like the idea is you start up a few machines, you have a lot of local disk out there, and then the state is highly available because we replicate the data, either with like 2 copies of the data, 3 copies of the data, and it's fully in your control. Obviously, in this case, you end up indexing the data multiple times. So if you write the data to one shard, and then you need to copy it or replicate it to another shard, you need to do the indexing process there as well. You need to think about persistency of the data. So for example, in many different data stores out there, you have the concept of a transaction log. So when you write data into a data store, you write a transaction log, almost like a log of the things that you're doing, while you maintain a more optimized version, like almost like an in-memory index or something that you flush to the disk periodically, and then you keep that in sync. And obviously, that transaction log exists in all the various shards that you perform the operations on. And then when you do the searches, it's the same thing. Like you pick one of the shards because they're relatively in sync in terms of the replication. Then you go and search on it, and the searches happen in the way that we know that Elasticsearch does it today. So this was a very common architecture, 10 years ago. The idea was that there's, you're running, you have a farm of servers out there, either on the cloud, because back then, obviously, EC2 and others existed, and you want to make use of it, very cheap servers that you keep on running, and you just, put in disk there and run and be able to scale your systems, in this case, obviously, search-based systems. And then things slowly evolved. For example, sometimes you care more about your data because it's what we call hot, right? For example, in many logging use cases or security use cases, data that happened in the last week probably gets accessed more compared to data that happened a year ago, right? It's like if suddenly production is down and we want to understand why, we're probably going to look 7 days worth of data versus looking a year worth of data. If someone suddenly we see a threat or we want to deal with alerts that we're getting because we're sitting in a security operations center, probably we're going to look at data that happened over the last 7 days, most of the time. Sometimes when there is we find something, sadly, for example, if suddenly there's a threat being identified, we suddenly need to look back into the data, but it doesn't happen as much. So hot tiers or hot data in Elasticsearch tends to be the one that deals with indexing. It needs to index the data and do all the processing, but also probably need to deal with most of the searches that you see on a day-to-day basis. And as data ages or becomes older, the requirements from it are different, right? For example, we might not write to the data anymore. It might be okay to store only one copy of the data versus multiple copies of the data. It might be okay to completely offload the data to S3 or like an object storage on cloud and do searches against it because it became read-only. That's the evolution of Elasticsearch and how it looks like today. So you can have a cold tier where the replication semantics are slightly different, or we can even have a frozen tier that is based on searchable snapshots. That's something relatively new in Elasticsearch over the past 2 years. That allows you to say the data exists in S3 and we can search directly against it. The stateless architecture of Elasticsearch takes that concept of searchable snapshots and everything else and takes it to the next level in terms of how we want to architect the system. To a degree, if you look at systems today, and we spoke about 10 years ago how data stores were being built. Today, if you look at data stores, and putting Elasticsearch aside for a second, and try to see how they're being built and how they are being designed, there's a huge movement to decouple compute from storage. And that's like part of the, if you're dealing with data stores, that's like the cloud native architectures and things along those lines. You see that happening in many of your popular data stores today that you look around from CockroachDB and a few others. Some efforts are happening around even relational databases and decoupling compute from storage in relational databases. But what does it really mean to decouple compute from storage? Because conceptually they're also decoupled on a single machine. You have CPU and you have storage, so they're decoupled. The idea is that you can scale both independently. Today, if you want to scale compute and storage in a system that replicates the data, then I need to add another machine, and that is both the compute and the storage that I have. But if I can decouple them, then I can scale them separately. And more interesting, at least on the cloud, I can scale down compute to 0 while still having storage be out there. And obviously, storage is significantly cheaper, especially blob storage like S3 and others, significantly cheaper compared to compute. That's a movement that is happening today in various data stores and systems. It's easier to implement in simpler data stores, right? Like things like data stores that only focus on one type of use case, like columnar store. For example, it's easier to implement that decoupling. In systems that are very rich, if you look at even just Elasticsearch or Apache Lucene that is powered by it, it has inverted index or FSTs. That's one type of access pattern. It has columnar store in dog values. It has a geo-oriented indexing mechanisms that involve, like it's a very, very rich experiences. Vector search is being added. So there's a very rich experiences, all come with like different type of requirements, which make it a very interesting challenge to try to implement this architecture. And that's the effort that we embarked, what was like about half a year ago or a bit more, to try to figure out if we can make it happen. And the good news is that we can. And we proved it with the POC. I think the team did a marvelous job in figuring it out. And I'll explain a bit how it works and the benefits that you get from it. So when you decouple compute from storage, you tend to have two tiers of work that you have. First of all, you treat the blob store, the S3, Google Cloud Storage, Azure Blob Store, or other systems as the main copy of your data. That's a mindset shift, right? It's like if before you said, I have 100 machines, each one has local disks, and the state of the system is the composition of all of these 100 machines, right? It's like this piece of data is stored twice here, this piece of data is stored 3 times there, and then when you bring it back up, we'll know how to recover things. And if you lose a few machines, that's okay because we have replication, we have high availability. In this case, we're moving all of that responsibility from Elasticsearch to the blob store. So we know S3 obviously does something similar behind the scenes in terms of replicating data and storing it and things along those lines. That's the only thing that it's focused on, or mostly the thing that it's focused on. And we're moving the responsibility of the actual storage of the data and persistency of it to S3. So when you look at the new architecture of stateless Elasticsearch, it's basically focused on the fact that the data is in S3. If I shut down all the machines that I have that are running or something along those lines, data doesn't get lost because it is already in S3. And then the question is like, how does it get to S3? And then how do we read it from S3 to search and things along those lines? And the typical architecture in that case, by the way, not only in Elasticsearch, in other places, is to have something that does the indexing or the ingestion of the data, ingesting the data, and then something that does the querying or the searching of the data. And it's similar in Elasticsearch itself. We're going to have an indexing tier that receives the request, does the indexing itself, and puts it into S3. And we have a search tier that is completely separate that allows you to do just the searches, like the regular searches that you would want to have. And obviously, the big benefits here that are just like straightforward. The first one is we can scale down the search tier and the ingesting tier to 0, and the data is still there. In the previous architecture, if we shut down all the machines, if we shut down all the machines and we just like let them go, we lost the data because we need to keep the disks around, right? Like we need to keep all of that data around. That's a huge benefit because it allows us to scale down to 0 if there's no usage. If there's very lightweight ingestion happening, we can only have a very small ingestion tier allocated to the ingestion itself. We don't have to have like large capacities. And then the same thing, I know your password.
No, you don't know.
I know the password of everybody in the company. We got a question. another story. We're a very distributed company, and sometimes the questions that we get are very interesting. And one of the questions that we got in our latest AMA was, did we install software to track people if they really work from home? And the other one of my, the other favorite stories that I have with being a distributed company, when we just started and, we work from, and, everybody joined in Zoom or things like that, but it's like, we're not that connected. So we had a Zoom room called Always On. So, people can join and just go on that Zoom and, chat and things like that because we're not connected. Then someone joined and we saw them on this Always On video. It was in support, I think. Always on, like from 9 o'clock until like 5 or 6. And then at one point we went to that person and asked them, like, why are you always on that Zoom video? Aren't you tired? Like, I would be exhausted being always on Zoom. And a person said, well, I thought it's called Always On because that's how you track that I really work. So that's like interesting things that you deal with when you're a distributed company. Anyhow, back to this. So the ingesting tier and the search tier don't have to be always on, which is pretty amazing because you can scale it down to 0, and you can also scale them based on needs that are decoupled from the storage itself. Today, if we need to do more indexing, we need to add more hot tier, and suddenly we add more storage, and suddenly we have to pay for more local storage, and like that coupling makes things more expensive. The other benefits that we're getting here is that we only need to do indexing once. In this case, if we want to have 3 copies of the data for high availability, then we index it on the primary shard and then index it twice more. So we're paying, or we're doing 3 times the amount of indexing that goes on. Now that's relatively common. If you look at Cassandra, or if we look at other, data stores that exist in this architecture, that's what you do. You do like operation-based replication. You do the same work that you do in other systems. Obviously, in a system like a search engine that tends to be more index-heavy, like tends to do a more indexing compared to other systems, you feel that pain more. So the exciting part here is that we only need to do the indexing once. We have a single worker that accepts documents, indexes the data, and then writes it to S3, and that's it. We don't have to go and do the work or replicate the work on more nodes because we rely on S3 as our storage system. Another part that is really exciting with this architecture is that we can scale the search tier in a very lightweight manner. So, things like, let's have 10 copies of a shard. If Elasticsearch, 10 copies of a shard that does searches. Why not? Now, you wouldn't think about 10 copies of a shard today in a system in Elasticsearch. Like, oh my God, this is like so many replications and I have to move the data around and all of these things. Not gonna work. But we can have 10 copies of the shard and do searches in the search tier, and that's not a problem. So it gives us a lot of flexibility in terms of the ability to scale searches to meet the demands of highly trafficked websites for searches to threat hunters running very complicated rules and things along those lines. And that's the exciting part. The other thing that it gives us is that this architecture doesn't have tiers in the concept of hot, cold, and warm. Like everything works the same way. It's almost like we took frozen in a conceptual manner. We took frozen, made it writable, and said, have at it. Like, that's it. Like, go and work across the board with it. So that really simplifies what you need to think about as a user. How does data ages, things along those lines, do we really need to do it? Today, we force you to do it because the architecture kind of like sits there in your face and ask you to think about it. But in this case, hopefully we can almost completely get rid of data tiers from that perspective. You might still say like after a year, after a week, drop some data, after a year, maybe do something else. So there might be like some actions that you want to take as data ages, but it won't be to the level of like hot, cold, or warm, or something along those lines. So this is a really exciting architecture. By the way, if you think about it, One of the other reasons why we wanted to get into this architecture is that it's a very lightweight architecture. Think about us running, tens of thousands of clusters, even more, on our cloud system today of Elasticsearch, many nodes, a lot of data. And every time something fails, we need to bring it back up. And then the whole recovery process is extremely expensive and slow, right? It's like you bring another node, it needs to recover the data from another place in order to make sure that you have the persistency of the data. When data moves, when you bring up another node, if you have two nodes and you bring up another node, then we need to reallocate the data and rebalance it and move data around and things along those lines. These processes are heavy, right? As you can imagine, because we're moving a lot of data around. In this case, we simply fire up more nodes and they just work against S3. So that's like much more lightweight operations that are going to happen. And as a result of it, your experience is going to be much better as a user. For example, we can scale up and down much faster compared to the previous system. Now, it's not all amazing. Like there's real significant challenges that we have, and maybe I'll mention a few of them. The first one is, well, if we have a single indexing tier, we have a translog. Like we need to keep things persisted for a duration of time to make sure that we don't lose data, and that gets replicated. We don't want to write the results of every single document being indexed into S3. That's going to be very expensive, and that's going to be much less efficient. So we want to somehow find a way to do some buffering so we can write more optimized data structure, either locally on disk, that's what happens in Lucene or in Elasticsearch, or pushing it to S3. So how do we solve that? We still need to have the concept of a transaction log, but if we have a single worker that writes to a transaction log, we might lose data if we write only to a single machine, because if we lose that machine and we haven't flushed the transaction log and have all that data set into S3, we might lose data. So how do we deal with that without complexifying the system? That's a challenge that we're trying to deal with now. There's multiple ways to try to solve it. From storing also the transaction log in a system like S3, or finding ways to store it in systems that are more optimized for it. The initial work that we're going to do is to try to put it also in S3 as a transaction log, and accept some of the latency aspects that comes from S3 for the transaction log. We'll see how it goes, and then potentially add more options to it. The other question that you have, and this is an interesting one. If you look at systems today that decouple compute from storage, then obviously suddenly doing full table scans becomes significantly more expensive, right? It's like if you have to go through the whole system, if you didn't put an index on the right field or something on those lines, and you end up doing a full table scan, you end up basically downloading everything from S3 and doing the query. So suddenly systems, data stores, and I'm not even talking about Elasticsearch yet or Lucene, systems that decouple compute from storage, suddenly how expensive a full table scan is becomes like at least 1, 2, sometimes 3 order of magnitude slower and more expensive, because someone needs to pay for all of that S3 APIs calls and list API calls and things along those lines. So one of the nice attributes that is pretty interesting to see how it ends up playing out, and we see today in our frozen tier, the fact that Elasticsearch and Apache Lucene are so good at indexing actually means that we can bring down much less data compared to other data stores that decouple compute from storage. If you think about one of the things that I probably said it 10 years ago as well, one of the really interesting characteristics of Elasticsearch and Apache Lucene is that you can take a document with 50 fields and index all of them. That was actually the default experience that you would get. Now imagine a system like that. Like imagine going to your relational database administrator and telling them, hey, let's have a table with 50 columns, and you know what? Let's put an index on each and every one of them. They're probably going to throw you away and say, like, there's no way that we're going to do that. Same thing with columnar storage systems, right? It's like you can't have your 50 attributes part of your key that you scroll through. Maybe you have one and maybe two, and you need to think about the ordering of it to do prefix matching or things along those lines. The amazing thing about a search engine is that you can index 50 attributes. Now, it's more expensive on ingestion time, yes. Surprisingly less expensive than you would expect to compared to putting 50 indexes on relational databases, but still more expensive. If you only index 2 fields out of a document with 50, it's going to be faster and require less storage compared to 50. But the nice thing that you can have with a search engine is that it allows you the composability that I'm having with ESQL and other places, and you say like, oh, I'll filter by host and then filter by this and that and what have you. All of the indexes are taken into account when this query is happening, which is, again, like not something that is straightforward. Sometimes we kind of like forget to remind ourselves that that's the case, but like that's something very unique in a data store. Like you don't see this thing happen. Another reason why you would go to your database administrator, you tell them, my query is slow, and they'll say, well, change the order of how you're running your SQL because you're not using the main index, or the database decided to use one index versus another, like let's go and make it happen. You don't see that in a search engine because it makes use of all the attributes. And that's really exciting on the search part. If you have a document and you decided to decouple compute from storage, your access pattern is suddenly much more optimized. Most of the time, you won't do full table scans because you can filter based on any type of aspect of the data. And that becomes much more important when you decouple compute from storage. And you take that and couple that together with the fact that we're only doing ingestion once now in a system, so you don't have to pay the cost of replication. And I think a stateless architecture that we deliver now with Elasticsearch is going to be even much more powerful, even just as a generic data analytics platform compared to other systems, thanks to these characteristics. So I get really excited about it. The other thing is that even with the fact that you have all the indexes and you can pick and choose and point and go directly to where the data is in S3 and only try to bring down as little data as possible because it's expensive and it takes time, you still need to have some form of local caching, right? It's like you still hit S3 and it's going to be slow. So one of the other challenges that we need to go and implement and figure out is caching. How do we do smart caching to make sure that we bring down to the local disk as a cache the right data structure that support your use case? If it's a system that tries to support search as you type, you probably want to have most of the data cached locally because any hit to S3 probably going to create a pause in the as you type experience. But then if you go all the way to, well, there's some threat data or security data that I stored, then I needed to store it for the last 2 years, but I barely access it, then let's make sure that that part is not cached. So that's the exciting part around how we're going to be able to play with these caching semantics and figure out how to do it. And if we do a good job, we kind of like manage to do it behind the scenes. So you won't have to worry about it. And based on access patterns, we're able to make the right decision. I think that we'll probably get mostly there, but we might ask you also for some hints. You'll tell us, hey, like this index, I think it's going to be frequently accessed. And we'll go, oh, it's frequently accessed. Maybe we'll put some weights there to make sure that it's more aggressively cached versus others and things like that. So that's mostly around this stateless architecture. It's going to be the foundation for our new cloud offering. So you go to our cloud and you're getting all of the nice things that you're getting with the existing system. And this one is going to be the foundation for a whole new cloud offering that is going to be a big part of our serverless offering. So something that tries to abstract even more away from you the physicality of the deployment and how it works, and more towards I just put data in and I can search it and hopefully it just works and it does the right thing. in a much more cost-effective manner.
My finger again.
I have your finger as well. Cool. Any questions? That's it. Yeah. Well, if someone wants to ask the question in French, we have a few French-speaking employees that can whisper in my ear in English.
Thanks for your presentation. Congratulations, because I think it's an innovation and a revolution. But we are a reseller, and I would like to know what is the new business model in terms of license.
Oh, for this, so the focus for this architecture initially is going to be our cloud. So it will be provided as part of our cloud offering. So as a reseller, the same way that you resell our cloud offering, you will be able to resell that. And then we'll need to figure out how do we take that and also provide maybe some of it on-prem. The reason why we focus on cloud now is that we want to move extremely fast. And obviously, this architecture heavily depends on blob storage. And we know what we're dealing with things like S3 and Google Cloud Storage and Azure Blob Storage. And those are the systems that we're doing the tests against now.
And Kubernetes on-prem?
Not initially. Not initially. This architecture initially is, we're only going to focus this on cloud. When it comes to on-prem, we have experiences with searchable snapshots, and there's complexity, significant complexity that comes with it. Pure storage, does it NetApp, things like that? Does it support the S3 APIs? Yes, no, what's the semantics? And here we're going to ask much more from the blob storage. And we want to go and ship it as soon as possible to our users. So the initial focus is going to be our cloud service.
By the way, we have the benefit of geo-replication, right, with that. We don't need the cluster replication, you know, that you have followers in followers and things like that.
So you can, conceptually, you'll be able to start search shards in other regions that work against that S3 bucket or whatever and benefit from that. That's probably going to be more expensive because then you might, because S3 is also regional, right, as one example.
Okay. Thank you, Shay Banon, for your presentation. So I have two questions.
Yeah.
So as I understand, for the stateless architecture, it's like we have a centralized core where everything is depends on the object store. But what happens if we lose the index store, for example, or the trace log in case of failure? And do we lose the data in the indexing tier and search tier side?
If you lose the blob store?
Yeah.
Yeah, if you lose the blob store, then you will lose the data compared to other systems. Obviously, a blob store has replication and has all the semantics that comes with it. One thing that I would say, if you look at a system like this, the previous one way to back up the data is we have the concept of snapshots in Elasticsearch, right? Where we can take the local data and snapshot it to S3. Actually, the searchable snapshots rely on that. You take the local data, snapshot it to S3. It actually works a bit like Time Machine. You can snapshot it now, and you can snapshot it an hour from now, and then it will mostly just snapshot the changes. So it's not like two copies of the data. So it's pretty cool, and it relies on this and how the system works. In this case, you will still be able to do snapshots. You probably want to snapshot it to a different object store and have backups of the data. And then the chances of you losing data are either because of high availability or something like that. And S3 high availability, for example, is pretty good or very, very, very good. Or because of human error, which you can also have today in this architecture, right? Like someone by mistake shut down three machines or something along those lines. And in that case, you can rely on the backups that we would have. Two questions. I'm waiting for the
last question is how our indexes are how lifecycle indexes are managed in this new architecture?
So you might still need to have like lifecycle indexes. For example, downsampling. So Nick is working on time series data, and some of the ways to reduce the cost of time series data is to downsample the data that you have. Move from I don't know, every second sample to a minute samples or to something along those lines. Somehow, you as a user will need to tell us, I want to downsample after a minute or after 10 minutes or after an hour. There's other things that happen as part of like the hygiene of an index or of a data stream. We call it the data stream now. That will still be there. So there will be, I suspect, some life cycle aspects, but hopefully there will not be any life cycle aspects to hot, warm, cold. It will just be the characteristics of the index. Downsample it, optimize it, things along those lines.
Thank you.
When will you release this new thing? And also, did you do comparison between the two architecture in terms of time speed for research, for query?
For query. So we did some tests. The interesting speed, and this image is taken from our blog post about it. So the ingestion speed is obviously, as you would expect. There's no it's at least twice faster. Because we remove the additional ingestion aspect, the search speed is as slow as searchable snapshots with no cache, or as fast as searchable snapshots fully cached. So we have a blog post with the performance around it because it really works in a very similar manner as searchable snapshots. When it's fully cached, you should expect to see exactly the same performance that you would have with SSDs. And we would want to give you the ability to do that. One thing that you'll probably be pleasantly surprised is that even with searchable snapshots that are not like fully cached or they just work the same way, it's surprisingly fast, compared to other systems when you go and query long-term data just directly on S3 because of the things that I mentioned before. There's one thing in terms of semantics, by the way, that is also a challenge that we're dealing with now. Today, in the previous architecture, I forgot to mention that in my talk, but I'll mention it now. In the previous architecture, you index data, and then you refresh, the lightweight refresh operation that Elastic has, and then it's immediately searchable. You can go into a search and you'll find it because it's on that same hot node, right? Here, it needs to go through a journey for it to be searchable. It's like it needs to be indexed, it needs to be flushed to S3, and as you can imagine, also the search tier needs to go, oh, there was a change happen. I need to take that into account and start to look at the new version of the data or something on those lines. Obviously, all of these things work in a very efficient manner because of the way that we store the data. It's like it will only going to be deltas. Think about it like a similar way that snapshots are very lightweight if you take one after the other. But that's still the case. So if you only do searches on the search tier, the freshness of the data is going to be different by definition. Like there's no magic there. So if, for example, before you could search the data after 1 second, maybe it will be after 10 seconds or something on those lines, the freshness of the data. We are thinking about adding some search capabilities to the indexing tier to maintain some of the like fresh query capabilities that you as our users might want. But we're trying to be very delicate about it because the less contention there is between indexing and searches, the better. So we want to make sure that we don't suddenly, even if we have a flag that says like really slow, only on the indexing tier search equals on, like we want to make sure that users won't turn this on for everything, and then suddenly all searches will go there instead of the search tier. So that's the thing that we're trying to balance. Did I answer your question about the performance? Yeah, cool.
Thank you for the talk. I have a similar questions about the replications. So we talked about the replication. We use it for the...
Whoever speaks, raise your hand. Okay.
So for the replication, we use it for the high availability, but we use it also to increase the speed of the search. So what will be the... In fact, I'm asking myself with the index store, if we will have the choice for some use case when we need to have a speed for searching, so to increase it, it will be useful to use this architecture, or will we have the choice to use the existing one?
So the existing one will still be around, even when we ship this, and that's why it's going to be a new offering on our cloud, and the existing architecture is still going to be around. My personal goal is that this architecture will completely replace the previous one, eventually. But the benefit of the existing architecture is that we can take it slow and try to figure out how to go. But like even today, in this architecture, like if you want to make search faster, you can much more easily make search faster in this architecture because you don't incur the overhead of additional replica shards that have to move data around and things along those lines. They're lightweight search shards to just like, you can say, I want to suddenly have 20 of them, and that's fine. They'll point at S3, they'll do their caching thingies, but they're very lightweight. They don't store the full copy of the data. You just run in a very simple manner.
Thank you.
Thank you, Shay, for the presentation. I have a question. For example, for normal user that is using a basic license of Elastic, I know you will not like it, but if you decide to move to the new architecture, you have to pay for a subscription for one of the cloud provider. So before he was using Elastic for free, but with the new architecture, he have to store his data on the cloud, for example, S3.
Yeah, so initially, this new architecture is only going to be available on Elastic Cloud, which means that you'll need to become a customer of ours on Elastic Cloud to make use of it, versus you running it yourself on self-manage. I think I explained why, like just from the ability to ship it as soon as possible, like we're only focusing on the major cloud providers. We're only focusing on, like, there's a lot of simplifications that we can do to try to go and figure it out. And then after we have a better sense about the architecture and the timelines and things like that, we will try to figure out what parts of it make sense to run on-prem, and then how do we expose it and things along those lines. I don't have answers about it now because, to be completely honest, like I'm only focused on shipping this as quickly as possible on cloud, and questions that I don't have to deal with, I'm trying not to deal with now because we need to be laser focused because this is going to be significant for our customers, as you can imagine, especially our cloud customers. Hopefully, this architecture, if you're not convinced now, will convince you to use our cloud, and that's a benefit to all of us, I think. You won't have to manage servers, and we would run it.
And the second question, when talking about the first subject with ESQL, this new architecture works well with ESQL because we have maybe we will have a cluster of search tiers, meaning that the SQL will run on the search tier and will collect data.
Yeah,
so it like this, or?
Yeah, exactly. It works really well with ESQL because, as you can imagine, you can now suddenly scale the search shards much more easily, and that query engine is going to be on the search tier probably. Not probably. It's going to be on the search tier for sure. I don't know about the interesting tier, but we're going to be on the search tier for sure. And like a typical system like this works really well with a proper query engine. So that's it's very, very complementary.
Hello. Hi. First, thanks for the presentation. I think it's red. So totally red. Yeah. I like your smile also. And then my question, first, I didn't quite get about the pricing model. I'm not sure to get how it goes. Yet I also want to know, well, before this, did you go over petabyte? And now, will you go over petabyte?
Yeah.
In terms of scale.
Yeah, understood. So first of all, in the previous like in the current architecture, not the previous one, the current architecture, yes, we have customers that are running above petabytes base storage.
Yeah, how did it go? Yeah.
It's more complicated than I would like it to be, but they're managing. Searchable snapshots definitely helps. Because if you think about it, searchable snapshots is a bit like stateless, the work that we're doing on the stateless part for all data that is not writable. So many of them that manage to move, let's say, 0.5 petabytes of data to searchable snapshot, they suddenly don't have to, the lightweightness of the cluster becomes significantly more, right? It's more lightweight. So it's still possible, but definitely in this type of architecture, large scale petabytes type storage or something like that is going to be significantly simpler to manage and run. In terms of pricing or something like that, as I mentioned, it's going to be initially available only on our cloud, on the cloud implementation that we have on Elastic. So you'll be able to go and deploy it. The exact pricing dimensions we have.
By nodes, by nodes or by, I mean, you know, petabytes, gigabytes, is it?
Yeah, we're still discussing because this is actually an opportunity to also improve our pricing model and have it more orient, for example, based on consumption. So you, for example, will only pay for the data that is being stored and maybe some aspect of the compute that is associated with ingestion and search that is like, you know, easy to scale up or down. The exact pricing dimension we haven't decided yet, but like that's the pricing dimension that we're thinking about for this offering.
So potentially like Splunk-like.
I don't know if it's gonna be Splunk-like, because the Splunk has like ingestion speed, ingestion pricing, and if you go to Splunk Cloud, their data platform is ingestion oriented, but now they're moving to worker nodes. The observability one is host based, so you pay per host and things on those lines. So I won't go and say necessarily Splunk-like, but more around data stores that have decoupled compute from storage and how they look like. Look at things like MongoDB serverless or CockroachDB or others. Like you pay for the data that is being stored and then somehow create an abstraction that represents how heavy you're ingesting data and how heavy you're doing searches.
All right, good.
Yeah.
Thank you.
Hello. I'm just here.
Oh, yeah.
Hello. I really like the new architecture, and like everyone said. So, so from what I understand is that the ILM will clearly disappear for a storage management, right?
Hopefully.
Hopefully. So, who's gonna do the storage management? First question. Second question. Second question is, it's not really clear. Can we do like multiple index tiers for one index store, or one index or multiple index stores for one index tier? If it's
okay.
Okay.
So I'll answer the first two because I'll forget the first one when you ask the third one. So I forgot the first one already, I think.
Storage management is going to do it.
When I was making a joke about the third one. So I think wait, what was the first question?
Okay. It's about the storage management. Who's going to do it?
Oh yeah. So hopefully that part goes away in terms of ILM, and then we would know based on access patterns what to cache. Because really the most important aspect here in terms of the tiering is what should we be caching locally to make sure that it's available for fast access.
It's all about usage.
Yes. Okay. Yeah. But we might, imagine that we power many of the largest e-commerce sites in the world today, right? And they expect to have like immediate availability and search as you type and things on those lines. Now, if they go and say, oh, start a few more capacity in your search tier, they would want it to be ready to accept like millisecond level responses, right? So it means that maybe we need to pre-fetch or pre-cache the data before we make it available to search. That part we might not be able to know as well as possible, and we might ask you to come over and give us some hints, where you'll say, for these type of indices, we expect 90% searches being found. I don't know, something on those lines. We don't know yet. We focus on those where we might want to ask you for some hints around it, and maybe that will be part of ILM. I don't know, but hopefully you'll see that the core architecture is exactly the same. Really, the question is like, how much do we cache per index? Versus this one where it really changes each time. Yeah, the second question?
Second question was like, can we do like multiple index tier for one index store, or multiple index stores for one index tier, or like to distribute it?
Oh, yeah. So the indexing tier, think about it like as a worker pool. So it has like multiple processes and it just performs the indexing. If you want to have more capacity, then hopefully we will auto scale to just satisfy it. And it's like, we'll just start more capacity and that's going to work. And then it's going to write to the object storage. The boundary of this whole thing is probably it was still in the design phases, but I suspect it's going to be similar to the deployment boundary that we have today on cloud. So when you go to our cloud, you create a deployment. It has Kibana, it has Elasticsearch, this and that. You can create another deployment. You can cross-cluster search across it and things like that. That will be the boundary for this one as well.
The third one I really like the last one. So now it's more storage based. Can we imagine something like how you say disk, like in disk how you say compute, like MapReduce, something like this? Can we imagine something like this?
Sure. So the data itself is stored in the object storage, right? So like that includes the raw data that you have, that includes all the indexing, data structure, the columnar storage, like all the things that represent it. And then searches basically are kind of like MapReduces. Like it's like the compute node that runs there, the way that Adrian described the query node, the query engine that we run in ESQL. Even just regular shards in Lucene, they're going to work against that data and then be smart around what do they fetch from S3 and keep locally versus not. It's probably going to be cheaper, yes, because you don't have to have everything represented all the time locally. So yes, the answer is I suspect that it's going to be cheaper. Yeah.
So we have two last questions, one in the back and one here.
Thanks for the talk. How do you address a multi-cloud strategy in one store?
It's actually very similar to the existing architecture that we have today. So typically, what we see in terms of deployment of Elastic in the wild is that people tend to deploy us next to where the data exists. So let's say you have an application running on Amazon, and you have another application running on Google Cloud, and another one running on Azure. You would have on our cloud 3 deployments: one in Amazon US East, one in Google Cloud, and one in Azure, and then you will store the data locally to the cloud, or even more importantly, locally to the region that you're running in. And that's part of like this data locality and making sure that data won't leave the cloud, because then it's very expensive, first of all, and other things that comes with it. We have a capability to search across deployments or search across clusters. We call it cross-cluster search. And it's really neat because we push down most of the searches to where the data is. So it's not like you stream all the data and get it or something like that. And then that's how our customers tend to do multi-cloud deployments. They deploy us next to where the data is on various cloud providers, and then use cross-cluster search to create like a single search box or a single dashboard or something like that that looks at all of it. That architecture is probably going to be the same here, because when you deploy on Amazon, you want to use the S3 store, again, like even within the same region, because then we don't have to pay for it, right? Like if you put the S3 store in US West and US East, you run the compute, that's going to be more expensive. So it will be in the same region. And then you create another deployment with Google Cloud Store as the backing system in that region. And then another deployment, and then be able to search across it the same way that you can today. That's the plan.
Last question here.
I have a quick and a small question. I'm here.
Yeah.
Do we expect the auto-scaling in the new architecture that you mentioned? The auto-scaling feature in the new architecture?
Yeah. Definitely. So a big part of this stateless architecture is that it means that it's much easier for us to auto-scale. And because things are more lightweight, right? It's like you, if you think about like auto-scaling this architecture, it's almost like an existential decision to add a node. Like I need to add another machine to add more capacity, but then it means that I need to go and move data around and shards and things along those lines. Like it's very expensive, the addition of a node or the removal of a node, because of all of the data movements that happen and the implications to a cluster that happen as a result of it. In this system, when you add workers, they're much more lightweight. Now, obviously, if you need full cache all the time, then you still need to download things from S3 and things along those lines. But even then, it only happens for that process. Like it doesn't affect the rest of the cluster. Like it doesn't suddenly go to another node in the cluster, tap it in the shoulder, and say, like, give me some data. I need it to recover. It goes to S3 and recovers the data. So it doesn't affect the rest of the cluster from that perspective. So definitely auto-scaling is going to be significantly simpler to implement. And our goal is that it will be a serverless experience. So auto-scaling will be out of the box. You won't have to worry about it. You won't have to go and manage it. You won't have to go and physically say, I want 4, I want 5. Now I'm under load, I need 8 or something along those lines.
Thank you so much, Shay. Thank you, Adrien, as well for the talks. Et merci à Peretis, à toute l'équipe, Ambre, Philippe, de nous avoir accueillis ce soir, d'avoir tout préparé. C'était formidable. Enfin, je ne sais pas ce que vous en pensez. J'adore.
Merci à vous, merci beaucoup. C'était un honneur pour nous de vous recevoir, de fêter tous ensemble un peu les 10e anniversaire d'un peu tout le monde. And I'm pretty sure in 10 years we will talk about this meetup too.
Ouais, sure. Thank you so much. The food now. Thank you.